Chapter 25 Statistical Thermodynamics Section 25.5 Electronic partition function and energy. The electronic partition function is this: Q sub electronic is equal to the sum of G sub I times e to the power of negative epsilon sub I of electronic minus epsilon sub 0 of electronic over kBt. Epsilon I of electronic is the electronic energy of the ith electronic state. Epsilon 0 electronic is the ground electronic state. And over here we take the difference between the ith electronic state and the ground electronic state. So we are essentially using the ground electronic state as the zero reference. G sub I is the spin multiplicity. Well, if you have a singlet, doublet, or triplet, G sub I is 1, 2, or 3. Here's an example. G sub 0 is 1 for H2, N2, helium-2, because for these three different chemicals. S is 0. 2s plus 1 is 1. They are singlet. So G sub 0 is 1 for the ground electronic states of H2, N2, and helium. Now for this H radical, fluorine radical, and OH radical, we have one unpaired electron. In the ground electronic state, S is 1/2. Therefore, 2s plus 1 is 2. It's a doublet. Then G sub 0 for these three radicals is 2. G sub 0 is 3 for O2 and B2. They are actually biradicals because in O2 you have 2 electrons occupying 2 degenerate pi star orbitals. In B2 you have 2 electrons occupying 2 degenerate pi bonding orbitals. In both cases, in the ground electronic state, S is 1, 2s plus 1 is 3, so we have a triplet for O2 and also for B2. Assuming the electronic energy spacings between the excited electronic states and the ground electronic state are much higher or greater than kBt, we then have this electronic partition function is approximately G sub 0. Because if you look at this series of terms, the first term is G sub 0 times e to the power of negative 0 over kBt. These two cancel in the first term. So really the electronic partition function is equal to G sub 0 if we can neglect all those other terms. The average electronic energy at temperature T relative to the zero reference, which is epsilon sub 0 electronic, is this. We use negative d ln q over d beta. And if, again, we can assume the electronic energy spacings between the excited electronic states and the ground electronic state are much greater than kBt. And then out of all those terms in the series, we need to consider only the first term, which is G sub 0. So Q electronic is roughly G sub 0, which does not depend on beta. Therefore, this part is just 0. The average electronic energy is 0 relative to epsilon 0 electronic. And over here, we can also call this thermal correction. The thermal correction to the electronic energy is negligible in most cases. This is just because nearly all molecules occupy the ground electronic state at room temperature or even at very high temperatures. In very rare cases, for example in a 3D transition metal, So over here, this d means d orbital. In 3D transition metal complex with nearly degenerate low and high spin states. And then we have at least two terms should be included in this electronic partition function. The first one is the ground electronic state. We have G sub 0, the spin multiplicity of the ground electronic state, plus G sub 1 times this exponential function. G sub 1 is the spin multiplicity of the first excited state. And this exponential function is this, e to the power of negative epsilon 1 minus epsilon 0 over kBt. So epsilon 0 is the energy of the ground electronic state. Epsilon 1 is the first excited state. So if the difference between the ground and first excited electronic states is very small or comparable to kBt, we need to include the second term in this sum as well.